Thanks to the organizers for letting me this opportunity to talk here. So today I will be presenting this recent work. It's in arXiv, manipulating phases in many body interacting systems with subsystem resetting. So this is done with these collaborators, Rupak Majumdar and my supervisor, Professor Shamik Gupta. So many body interacting systems, they often exhibit rich phase behavior. So in this case, so there is some ordered phase at some parameter region of the system, let's say some temperature, and as you increase the temperature, so the system goes through a phase transition, it goes to a disordered phase. So in this figure, you can see that as you increase the temperature, the pattern gets changes. And now you can ask what is the measure of the order. Like in case of magnetic system, you measure the order with this m, which is the 1 by n over sum over the spins, and then the vector r, it is for the non-equilibrium, some nonlinear oscillator models. I will talk about Kuramoto oscillators, which is the effective sum of the phases. So now our question is, can we control the phase behaviors? And here comes the subsystem resetting protocol as a minimal and partial intervention. This can lead to dramatic impacts, as I will show, and this is a new route to drive, tune, or suppress phase transition. So here I show for this protocol for 1D spin chain and Kuramoto oscillators. So let's start for the spins. So at very small temperature, you see there is a fixed temperature of the system, and the system evolves for some time and it reaches steady state. So at some random time t1, it is in some configuration, and then so there you reset, and you do not reset the full system, you reset a subpart, and that portion is kept fixed, and there is the non-reset subsystem. And you ask what is happening in this behavior, like what happens at steady state to this non-reset subsystem. And again, this is Kuramoto oscillators. So this is the oscillators evolving, and at random times, those rare oscillators are getting reset to a particular phases, and I am asking what is the effective order happening in the rest blue oscillator, which is I am calling the non-reset subsystem. So in the plot, this is if there is no reset, the whole system order parameter goes to a very low synchronization value. But if you introduce this subsystem reset, you can see if you see the if you probe the order parameter of the non-reset subsystem, it gets to a higher value. And this is the order parameter of the reset subsystem that is getting reset at each time. So here I study in diverse study this protocol in these diverse fields. This is one is this equilibrium mean field models, Blue memory Griffiths, then again this equilibrium nearest neighbor and mean field model, Cardan-Nagel, and then this is the non-equilibrium model, of course, noisy Kuramoto model, which has both Cohen's disorder and annealed disorder. And all these models have a common feature that in the parameter region, these have both second order and first order phase transition. Like for these spin models, they have this phase transition from ferromagnetic to paramagnetic, and this Kuramoto model, it goes from a synchronization phase transition. So here we ask the order parameter, so the order parameter of the reset part and non-reset part, and we ask what happens to the order parameter of the non-reset part. What we can tune is the size of the reset subsystem, and we can tune also what is the reset configuration of the reset subsystem, and of course the rate of resetting. So what you can see, so I study for the lambda going to infinity, lambda is the reset rate, and then finite rate of resetting. If the resetting rate is too fast, then you can write the Hamiltonian of the non-reset subsystem as this effective part. And here you can see that this is, I'm talking about this BEG model, you can see the effect of the reset coming as the effective field to the old model. And what we are seeing here, that this is the KT phase diagram, and then I have the new phase diagram at k equals to this value, where the Bayer model shows only the second order phase transition. But if you introduce this subsystem resetting, you plot this at one parameter value of k, and your system has both second order going to a tricritical point, first order phase transition, and crossover. So blue line is the first order transition, dashed line is the second order, and crossover. So in this, where the system allows only a second order phase transition, you have second order, first order, and crossover. And here I am resetting the reset subsystem with the zero magnetization. And as you increase the magnetization, this kind of behavior happens. So you have newer phases, like in this region, your reset subsystem magnetization has some value. And here you have this kind of first order phase transition and two distinct crossover region. Here this kind of crossover, and here this kind of crossover. And this generic feature happened. And this is the whole phase diagram. Like this was the bare model phase diagram, and this is the newer phase diagram, where these features of the, these are the features of the order parameter behavior in the non-reset subsystem. And this is the phase diagram, this is the order parameter behavior when you have finite rate reset. So yeah, I just explained here that when lambda is very small, that is the bare model with reset, and as you increase, it goes through this and effectively reaches to a infinite rate limit. And then again, we can do this same analysis for the Kuramoto model, both for finite lambda and infinite lambda, but I am not like bothering you with the whole analytical details. But yeah, what you can see in this noisy Kuramoto model setup for finite reset, you can see that from left to right, I increase the lambda, and you can see that introducing this subsystem reset, you see the order parameter showing different behavior. Like you can see the change of critical points, the behavior of the phase transition going to second order to first order, and so on. And here also you can see that this is that the phase diagram behavior at infinite rate limit, infinite reset rate limit, that is very similar as I showed in the BEG model, but there are some little bit difference in the order parameter behavior. But overall, this how the phase transition changes as you change the resetting rate, that is grossly similar. So at a glance, there is memory effect in non-reset subsystem, which precludes linear theory. But of course, despite challenges, we have explicit analytical result and also validated with numerical simulation for Monte Carlo for spin models and RK4 for Kuramoto model. So we have robust control over phase diagram in diverse setups. But what I have not tell you that so far, all these models are long-range interacting models. So you need extensive number of connection between all the parts of the system. So physical application is like, there is a group by Peter Tuss in Stanford University. So he uses these coordinated stimulants to fingertips in Parkinson's patients treatment. And this is a very effective treatment to Parkinson's disease, and you can see his TED talk online. So epilogue is I can show, and thank you for attending. Yeah.
Questions?
Hi, nice presentation. So your models are long-range interacting, right?
Yeah.
So usually without resetting, they show ensemble inequivalence.
Of course.
So have you checked after resetting how this inequivalence ensemble is affected?
We can check it, but I think it will remain there because you see that, so there is, in reset, I think that will remain, like that is a separate part of the talk. You can take it also, but that will remain. If you have first order and second order phase transition retaining, I think that will remain. So there will be inequivalence still there. But so far, our focus is controlling a very small region, what like effect you can impose in the rest part of the system.
Very nice talk. Just one question. In the lambda tends to infinity limit, the very high resetting rate. So how can you track it, the numerical simulations?
So I put it
Okay.
like
Very high.
lambda going to infinity limit, I just disturb the system, resets the system.
Okay.
I just resets so fast and fast.
Okay.
If I
When you use RK4, like you have to keep the DT very small or something like.
DT is always small. DT
Yes.
is the like normal evolution, but the reset rate, like when Sanjeev talked, so like the exponential from
Okay.
exponential distribution, you are taking the intervals.
Okay.
You put lambda very
Like,
high,
okay. I see.
then intervals are very small. So reset is happening at
Okay, like kind of Monte Carlo kind of the Poisson process. You are taking the intervals from an exponential. I see. Thanks.
Yeah, just one question. So
yeah.
maybe you mentioned this. So in subsystem resetting, you won't have a renewal formula, right?
No.
So is
Because
there,
you have like memory effect.
yeah, so it'll be non-Markovian.
Non-Markovian.
So
Exactly.
is there any work where for a very simple system with subsystem resetting, there is some analytical progress?
So analytical, like Kuramoto model, we have explicit analytical results.
But where is the, have you used the renewal form?
No, not renewal. So you can see that this is the Fokker-Planck equation with the resetting. So normally what you have, this is the diffusion part, and this is minus lambda p, that is the normal rate, and this is the whole kernel now, which is the memory dependent kernel. So one is, this is coming from the reset part, and then this is coming from the non-reset part.
So that is the part of the system which is not resetted.
Yes, non-reset part.
And you have analytical solution for that equation.
Yeah, we have explicit analytical solution.
Okay.
Because
But then there must be presumably some renewal equation which can produce this, or it's not clear? Some non-Markovian renewal equation that
renewal
can
equation you can take, but for effectively for renewal equation, you need the propagator, free propagator. So, but in case of interacting systems, free propagator is not there, right? But we can free propagator.
So I'm talking about the fact that the whole system is not reset.
Yeah.
The fact that only part of it is reset, that makes renewal equation harder, right? Not just the free propagator.
Yeah.
So,
of course.
Is that correct?
I don't think memory dependent equation can be solved renewally.
For any model?
No, I don't think so. Yeah, that will be very hard. But even for this non-trivial setup, we have the result. We have result for steady state, but also we can track it for dynamics, like how order parameter behaves in the transient time. Thank you.
Let's thank our speaker.
Thank you.
So this is time for coffee break. We'll resume at 11:50.